Have you ever just looked at something complex and beautiful in nature and wondered, is there a really simple rule hiding underneath it all? Well, that's exactly what we're going to explore today. We're on the hunt for the hidden blueprints that create perfection.
And we're going to start with something you've probably seen a million times. When three soap bubbles float together and connect, they don't just randomly mash into each other. Nope. They follow a very precise, super efficient rule. But what is it?
Then we're going to take a giant leap. What about something that looks way more complicated, like this, a perfect dodecahedron? It seems impossibly intricate, right? But what if I told you its entire structure, its secret blueprint, could be written down using just a couple of numbers? What's the secret there? We're going to figure it out together. And the best way to do that is to break it down and tackle it one dimension at a time. We'll start in the flat world of 2D, move through our familiar 3D, and even take a peek into the mind-bending concept of a fourth dimension. All right, first up, let's look at that perfect connection in 2 dimensions. This is where we uncover our very first hidden rule, and it is beautifully elegant. So this puzzle actually has a name. It's called the Fermat point problem, and it's a classic challenge in geometry. The goal is to find that one single magical spot that creates the shortest possible network connecting 3 other points. Okay, to make this real, just picture 3 posts stuck in the ground. You've got to connect all 3 of them to one central hub. The question is, where do you put that hub to use the absolute least amount of rope?
And the answer, the whole solution, boils down to this one perfect number, 120 degrees.
It turns out the most efficient spot, the one that uses the least amount of rope, isn't random at all. It's the point where the 3 connecting lines meet at exactly 120 degrees from each other. Our source material calls this a geometric law of closure. It's the path of least resistance, and it's the exact same rule those soap bubbles follow. But here's the catch. This beautiful rule has its limits. If your 3 posts form a triangle, where all the corners are less than 120 degrees, you'll always find that perfect sweet spot inside the triangle. But if one of those corners is 120 degrees or more, the whole solution changes. The optimal point literally collapses and snaps right onto that wide corner. So the rule has a very clear breaking point. Okay, so we found our hidden rule for 2D. Now let's level up and see if we can find a similar kind of simple blueprint when we build a masterpiece in 3 dimensions. So our new question is this: can we find an equally elegant recipe for a 3D object? Does a shape that looks as complex as a dodecahedron have its own simple, hidden instructions? Amazingly, the answer is yes. And the recipe is way simpler than you'd think. The entire blueprint for a perfect dodecahedron can be built by mixing and matching just these few values, 0, ±1, and the famous golden ratio, phi, along with its inverse. That's it. That's the entire ingredient list. Seriously, think of it like a cooking recipe. You take those simple ingredients, and by arranging them in different combinations, like +or-1, 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 you get the exact X, Y, and Z coordinates for every single one of the 20 corners you need to build the shape. So how do we actually know this recipe creates a perfect shape? Well, mathematicians have this rigorous 3-step quality check. First, the metric check. They prove that all 30 edges have the exact same length. Step 2, the face check. They confirm that all 12 faces are perfectly flat. And finally, the sphere check. They show that the shape can be nested inside 3 perfect concentric spheres, one that touches all the corners, one that touches all the edges, and one that touches all the faces. This recipe passes with flying colors. All right, now for the biggest leap of all. We found the rules in 2D and 3D. So what on earth happens if we try to extend this blueprint into the 4th dimension? Now, before our brains melt, it is really important to be clear about what we mean. To quote the source material directly, these are geometric extensions, not as claims about reality. We're not saying a 4th physical dimension exists. This is a purely mathematical thought experiment. So yeah, you have to think of it like a game of pure logic. We have this beautiful blueprint for building a 3D object. The question is simply, can we extend those rules in a consistent way just by adding one more coordinate? And the way you do it is almost comically simple. You take any corner from our 3D dodecahedron, its x, y, z coordinate, and you just tack on a 0 at the end. That's it. Now you have a 4D point, x, y, z, 0. All the original 3D relationships are perfectly preserved in this new, bigger space.
Now, this is where it gets really interesting. We take our dodecahedron, we make an exact copy of it, and we place them parallel to each other in this 4D space. They're separated only by a distance along this new fourth axis, which we can call W. It's like having two identical objects floating, one just above the other, in a direction we can't see.
Of course, we can't actually see in 4 dimensions, so we have to visualize it by projecting it back into our 3D world. If you use an orthographic projection, it just squashes that 4th dimension, and the two shapes look like they're sitting right on top of each other. But if you use a perspective projection, which scales things based on how far away they are in 4D, something incredible happens. The two shapes appear as one nested perfectly inside the other.
So we've gone on this pretty wild journey through dimensions, uncovering these simple, elegant rules. But you might be asking, so what? Why does any of this actually matter?
Well, think about the thread we followed. We saw how a single angle, 120 degrees, creates the most efficient connections in 2D. Then we saw how a simple recipe using the golden ratio builds a perfect solid in 3D. And we even saw how a simple layering idea extends that same structure into 4D. There's this amazing pattern of simple rules creating complex beauty.
And this isn't just some abstract game for mathematicians. Having these exact coordinate blueprints is incredibly useful. It helps people explain complex ideas, it gives computer models the precise data they need for simulations, and it allows architects and designers to use these perfect geometric forms in their work. And that leaves us with one last big question. If a couple of numbers and a single angle can define such perfect, complex shapes across multiple dimensions, it really makes you wonder, what other simple, elegant blueprints are out there hiding just beyond what we can see, just waiting to be discovered?